Alright, hello. This video is about Boyles Law. Boyles Law specifically looks at pressure versus volume and how one changes and the other is affected by that. So first we're going to look at the math, which is on the right side, and then we're going to look at a real-life application on the left side. Let's take a look at the math first. I have two ways to graph this. You can see pressure on the y, and this is inverse volume on the x. On this other graph on the right, there's pressure on the y still, and this is just plain volume. Either way you look at it, it's the same relationship. Take a look at the one on the right. As we increase the volume, that means going this way, we can see that the pressure has decreased. That's an inverse relationship. The same thing is actually happening on the left side, because if you think about a big volume, like 1 over 100, or even bigger volume, 1 over 1,000, as you get to a bigger and bigger volume, an increase in volume, the number actually gets super, super small. So here would be a really big volume at this side, and we can see that's a really low pressure. So as you increase the volume, you will decrease the pressure. An inverse relationship. Let's take a look closer at the math part. If I take two data points on this right-hand graph, maybe we'll take this spot right here and this right here. I'll call this one P1, V1, and this one P2 and V2. Now they both follow this relationship. I know you can't really read that really well, but that's a negative 0.96. So if I take that actual equation, y equals 895 x to the negative 0.96, which really rounds to negative 1. So suddenly that becomes y equals 895 over x. I'm going to change x and y to what they actually are in the relationship. Y would be p equals 895 over x, which is my v. Now I'll say, now that I have this relationship between p and v, p equals 895 over v, I can switch around a little bit more to say p times v equals 895. Well, I'll just take one data point, my P1, V1. P1 times V1 equals 895. And at the same time that happens, P2 times V2, my second point, equals 895. Well, if they both equal 895, I can say that P1, V1 equals P2, V2. And that right there is Boyles' Law. Here's all the math part with Boyles' Law. They're an inverse relationship. What this allows me to do also, now that I have an equation, I can solve for any data point that I want. This data actually came from a syringe that was filled with gas, and then we just changed the volume and recorded its pressure. So if I want to take something like data point, if I look on the right here, at 62, I know you can't really read it very well, but there is a pressure at 62, whoop, right here. There's a pressure of 62 and a volume of 15. I can hardly read it either. I looked at the original. You'll have to trust me on that. So if I call P1 62 and P2 and V2 15, I can actually plug it into this equation here. I can see that P1 is 62, V1 is 15. So that's like having the syringe at a certain spot, and then I'm going to take the syringe at the mountain. At the top of Mount Everest, it has a pressure of 33 kPa, and this is all in kPa. So I'm going to change the pressure to be 33 kPa. What does that do with my volume? If I do some math, boop, 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 I get a volume in the end of 28 milliliters. You can see that as I add a high pressure, I add a low volume, and at a low pressure, I have a high volume. Why would that be? Taking a look over here, I've got a bag of chips, and it's actually really, really inflated. It might be hard to see. But what happens is, on a mountain, if we're standing right here, we're at a certain pressure, but as we walk up the mountain and go to the very top, like at Mount Everest, the pressure has decreased. So that pressure is high at the bottom. So let's say we're living in a world where the pressure is high at the bottom. First, you've got the bag of chips, and the pressure on the outside is equal to the pressure on the inside. That's why the bag of chips just kind of sits there, looks like it's doing nothing. If the pressures are the same, that means the molecules have the same kinetic energy, not the same kinetic energy, well they will because it's the same temperature, Boyles doesn't apply there, but the pressure on the inside is equal to the pressure on the outside. And that's why the bag isn't inflating or deflating. Well, as you walk up the mountain, you have suddenly taken the pressure and you have decreased it. Because as you go up the mountain, there's less air above you up here. There's less air above you, there's less weight on you, there's less atmospheric pressure. So my pressure has now decreased. Well, suddenly, the outside pressure is not equal to the inside pressure. So my inside does not equal my outside. And the world's not okay with that. If the pressures are unequal, they'd have to change things. The only way to change things to make the pressures the same is to suddenly take the volume and increase the volume. If you increase the volume of the bag, then the molecules are no longer hitting the sides as frequently as they were before. They're hitting them as hard because they're moving at the same speed. The temperature, we're assuming, hasn't changed. but they're going to hit the sides less often. If they hit the sides less often, this correlates to a pressure being decreased. So my pressure inside is now decreasing, and it will decrease until, it's going to increase. Oh my gosh. My pressure inside will decrease until the pressure inside is equal to the pressure outside. And the reason that the pressure was able to decrease is because I was changing the volume to make it bigger. They were hitting the sides less often. Whew, I hope I fixed that. Alright, there's your real world application and the math. I hope that helped.